All right, so you all heard it. You all been warned. This meeting is being recorded. All right, so I'm actually going to go ahead and switch to my other headset and talk to you through so that you can see the screen or the whiteboard here. So give me just 1 second here. Okay, so now hopefully y'all see the whiteboard, but can still hear me. Give me a quick thumbs up if that's the case. We're all good? We're all good. All right, cool. So this is Mat104, trigonometry. So I always like to start here with any class, is just sort of talk about what it is and what we're going to do. So mathematicians are notorious for naming things exactly what they are. I don't know if you've noticed that. Like, think about this. What's a linear function? It's a function whose graph's a line, right? So we're kind of really obvious in what we do. And so trigonometry is no different. So let me just give you a little etymology, a little bit of where the word comes from. So I bet you know some of these things. Like this guy, try. What does try mean? Oh yeah, I love it. I'm getting a lot of people giving me 3 fingers up, right? So try means 3. Duh. Okay, so something about 3s. You may know meter, metric. Anybody know what that means? This might be a little bit harder to sign. Anyone want to throw something out in the chat? What do you think, metric or meter? All right, yeah, cool. Amber just threw in measure. Yeah, that's exactly what it is. I don't know if you know this, but like when we talk about the metric system, it's the way that we measure things. Okay, so we're measuring something that's in 3s. All right, so then there's the gone. Now this one, I bet you don't know what it is. You probably think you do, but you don't. Talk about a trap, right? So anyone want to make their guess for what they think gone is, knowing that it's probably wrong? All right, so let's see. So Adam, you just threw out polygon. Yeah, it's the same suffix there. So like, what's a polygon? All right, so Kai is saying shapes. Good. All right, so you think about like polygons, think about ones we know. Hexagon, pentagon, right? Octagon for you UFC folks. So what are those prefixes telling you? All right, so multiple sides, says Adam in the chat. Yeah, so usually people think that when we talk about like a hexagon, it's a 6-sided figure. And that's why I was saying, you think you know what it is, but it isn't. Because gon doesn't actually mean sides. It means angles, right? So it's a little bit of a switcheroo. So let me put here, so angle. So trigon is literally something with 3 angles. Okay, we also think of it as something with 3 sides. So it's a 3-sided figure, also known as a triangle. So trigon literally is a triangle. So trigonometry is triangle measurement. Yay. So what are we doing in trig? Well, we're actually not going to be measuring triangles very much. We're going to be doing it a little bit, but there's a way more to trig than triangle measurement. But this is how it started historically. And you can thank the Greeks for coming up with this. They were big geometric folks. And one of the things that they looked at was trying to measure triangles. So basically, we need to start with just how do we measure triangles? So let me go ahead and put a triangle up here. And let's talk about what we're going to measure. All right, so there's my random triangle that I'm drawing for today. And suppose I just asked you to measure this. What kind of things might you measure? All right, so Amber just threw out side lengths. Yeah, that's a great one. One of the things that we might be interested in is how long are these lengths? Like when we go from one of these points to the other point, how long are those things? So that was definitely one thing that they were interested in with triangles. And when we get to the point at the end of this class, when we're quote unquote solving triangles, we're going to be looking for the lengths of the sides. So I'm going to go ahead and put that here as one of the things we're interested in. All right, so we're going to be looking for the lengths of the sides. Now, that's pretty easy to do. All you need is a ruler, right? And even if you don't have a ruler, you can use some sort of a makeshift device to still figure out those lengths. Like I could just take this piece of graph paper, for example, put it up here, and just kind of make my mark from there to there, and I know how many little boxes it is, right? I don't even necessarily need to know the size of these boxes. So measuring lengths is pretty easy. But there's a lot more we could measure. What else could we measure in a triangle? Other ideas? Got a couple of people here throwing out angles. All right, so angles are these guys right here. I'm going to go ahead and put just a little bit of an arc. You'll usually see little curved lines like this showing angles. Sometimes you'll have 2 versus 1 to designate that it's a different angle. But all right, so these are our angles. Now, angles really are a separation, right? They're how far apart are these legs. But you can notice that this is a challenging thing to actually define how big that angle is, because if I said, how far apart are these 2 legs? The answer kind of changes. Because if we're just going to talk linear distance, if I were to take 2 points, let me make them nice and big here. It's like this one and this one. The distance between those 2 points is very different than the distance between those 2 points. So we can't use a linear distance to talk about, you know, this separation. And so what's kind of interesting is that we measure angles by looking at rotation. And I know that seems kind of weird, but basically the idea is if we have, say, our one side, we want to think about how far would we have to rotate it until we were to reach the other side. And what's nice about defining it as a rotation is it doesn't matter where you are. All we have to do is think about taking that entire side and sweeping it. All the points rotate through the same portion of the circle. It's a different size circle, but gives us a different, well, maybe not different, a better way of actually describing the angle. So angles technically are a collection of a point and the 2 rays that come out from it. And so that right there is the angle. It's defined as 2 rays that are coming out of a point. And just so you know, this point is called a vertex. So when we have polygons, like the triangle itself, the points where these angles come together, those are all a vertex. As a group, they're called vertices. So you've got a vertex, and then you've got your 2 rays that come out from that vertex. So we're going to really be curious about how big these angles are. So we're going to have to figure them out by rotation. All right, so cool. We can figure out lengths of sides. We can figure out the size of the angles. Let me put that down here. Can you think of other things we might want to figure out about a triangle? Measure, specifically measure. All right, so Adam throws out the center. Center of the triangle is actually a very interesting point, and it's used a lot. Let's see, Amber just threw out area, so did Bella. Okay, cool. So the area, how much, you know, space is there inside that triangle? In terms of application, that's actually pretty big. Think about like a triangular piece of land, something like that. Let's see, Kai just threw out, ooh, bisectors. The bisectors of the angles. Turns out that the bisectors of the angles have something very much to do with the center of that triangle. So yeah, we can do all that great stuff from geometry and try to measure them. So even there, you can start seeing that trigonometry is kind of a big deal. When we just talk about measuring triangles, there's a lot that can happen. All right, well, we're going to concentrate on lengths of sides and sides of angles, because that's sort of classically what was done, and tends to be the more important aspect in terms of applications. But we will address things like area and that later. All right, so I want to concentrate on angles a bit, because you know how to measure lengths. That's a no-brainer. So let me start with just some terminology that we're going to use. I call this the geography of the angle. Just some things that we want to talk about. Now, I mentioned that we're going to start with some side, and we're going to go ahead and rotate it until we reach the other ray to form our angle. So we already have the vertex. This side right here, the first one that I drew, we actually call this the initial side. You may remember that I told you that mathematicians name everything exactly what they are. Well, that's the initial side, because that's where we start. Yay. All right, so that's our initial side. And then where we end up, this is called the terminal side. All right, so we go from initial side to terminal side. Makes total sense, right? All right, now, mathematicians are also really organized, and we like to be specific, and we like to do the same thing the same way every time, right? We're very procedural. We like having the recipes, the algorithms. So the other thing that we're going to do when we go to start dealing with angles is we're going to make it so that our initial side is always pointing in the positive x direction on the plane. So let me go ahead, I can do this down here. Oh, and please let me know if I ever get too low on the screen and you can't see it, give me a heads up, all right? I think I have a pretty good idea where that line is, but just in case. So here's our good old, right, x and y axes. So you know this from regular old graphing of everything. Well, when we do angles, we're always going to put the vertex at the origin. Okay, so at 0, 0, that's where we're always going to put the vertex. We're going to put the initial side in the positive x direction. So think of that positive x-axis as the initial side. And then we're going to rotate in a counterclockwise direction to our terminal side. All right, so Bella, video is a little too low. What do you mean by that? I'm drawing too low? All right. I'll redraw that up here. All right, thank you for that, Bella, by the way. So there's our initial side. This is going to be our terminal side. And we're going to go in a clockwise direction. Or sorry, counterclockwise direction. And this is going to be something that might take a while to get used to. And that's the fact that we're going to go counterclockwise. We are really used to in our everyday life doing everything in a clockwise direction. Now we want to go counterclockwise. All right. Why? Well, because I can give you the dad answer, because that's how we decided it's going to be. But when we rotate in a counterclockwise direction, from the initial side being on the positive x-axis, we actually call this standard position. So angles are in standard position in this way. And so this is how we're going to always want to start them off. We're going to put the vertex at the origin, initial side on the positive x-axis, and go this direction. Now, I mentioned that we're going to go counterclockwise, but what if we went clockwise, right? There's nothing that says we can't do that. If we do that, all we have to do is realize that the angles, since we're going a different way, we're just going to make them negative, all right? So the way that this is set up is that positive angles is a counterclockwise rotation, and negative is when we go clockwise. So it might feel a little bit weird to have negative angles, and I don't blame you, because especially from we're drawing a triangle, shouldn't be negative. We're going to want to allow for negative angles later. So just realize that positive and negative just mean the same thing, just going opposite directions. And that's not new to you. Think about a real number line, right? Positives go to the right, negatives go to the left. So what's the difference between a +5 and a -5? Well, one I went right, the other one I went left, okay? So it's kind of the same thing. Difference between a positive angle and a negative angle, like if we have an angle of 4 versus an angle of -4, it's the same rotation, just opposite direction. All right, so now that we kind of have that set up, we need to talk about how we actually measure it. So I'm sure you already know about one of these because it kind of invades our life in all kinds of places. Just watch a snowboarding competition and you know the one of them for sure. But when we measure angles, we use two things. We use degrees and we use radians. So these are just like when we measure lengths. We can measure in inches, or we can measure in miles or kilometers or parsecs or whatever you want. Just like that, with angles, we have two main ways of measuring them, degrees and radians. Now, we'll talk about degrees first, because I'm sure most of you know a little bit about them. And since angles are all about rotation, the way these things are defined is what happens in one complete rotation. So, because I bet you know this, someone in the chat window type me how many degrees are in one rotation. Yeah, see a bunch of them coming. It's 360 degrees. So we know this one. And like I said, this is where you get this in like the snowboarding and all that, because they'll talk about someone doing a trick and they just hit a 760 or 720, right? Or a 1080 or things like that. And that's basically just telling you how many complete rotations they did. But the way that degrees work out is one rotation is 360 degrees. All right. So, all right, so Adam, what does that mean? 760 to face plant? Do an extra 40 degrees and then on their face. I definitely watch the Olympics, but I am not an expert at all on anything snow sport related. Anyway, so 360 degrees, that's our full rotation. So what that allows us to do is start getting some values for specific angles, right? So think about this. If we do a full rotation, we're going to put our initial side in the positive x direction. And what I'm going to do is I'm going to spin it. So think of my pen here as my side as I'm rotating it. So I'm rotating, I'm rotating, I'm rotating. And I come all the way back so that my terminal side is on my initial side. I've done one full rotation. That right there is your 360 degrees. So a 360 degree angle looks kind of weird because there isn't a second ray. Well, it turns out that I could have gotten that same thing by not rotating at all, right? What if I had just put this right here and not rotated, I've done none of a rotation. So similarly, if I have just the one ray like this one would be 0 degrees. It's not been rotated. So if you look at these two, they look exactly the same, but the way that we make sure that people understand that one of them, there's been a rotation, the other one hasn't, is we actually draw this little circle with the arrow. And that specifies we went around once. So let's do a 720, right? Let's say we go and we spin around twice. So for a 720, we're going to come around one full time. We're going to go around a second full time. And that's how we would actually represent 720 degrees. So pay attention also to the little curves here, because they'll tell you how many times you've gone around to get to that place. Similarly, we could have gone backwards, right? What if instead, let me draw, I think we can see it over here. I'm still going to do one cycle, but I'm going to go backwards. So I'm going to go clockwise. This would be a minus 360 degrees. But notice that for all four of these, the terminal side ended up being where we started. Well, yeah, that happens. But we got there in a different way, right? If we go back to the Olympics, let's see. Let's say you put the arrow on the inside for negative. Oh, the fact that it was inside or outside, I think it was because I was getting lazy. It doesn't really matter. What matters to show that it's negative is the fact that, yeah, I'll make it so that they're all looking the same-ish. All that matters to show that it's negative is that that arrow is approaching from the top. It's coming from a clockwise direction. Does that make sense, Adam? Okay, cool. All right, so we have
I just wasn't sure because, I mean, if you just kept going, you would continuously go on the inside and you'd run out of space. So I just wasn't sure if that was like a signal to show that it was negative or not, or yeah, so that was my question.
Yeah, okay, good. No, it doesn't matter. Like I said, I think I was just getting lazy, and usually you don't have to worry about running out of space because there's only going to be a handful of rotations, but you're right. If I wanted to keep going, I would want to make sure that it progresses further and further out. Okay, so real quick, while I'm at this point, let me just mention that we have a name for this kind of angle. We call these things coterminal. All right, and what this means, again, look at the word. What does co tell you? We use that word to mean sharing, right? When something is co. So coterminal angles, these are ones whose terminal sides are at the same place. So I'm going to write here, the terminal sides are at the same location. So basically, it just means we went about a different way of rotating to get there. Right? We, uh-oh. Okay, good, it's back. All right. We go a different way of getting to that location. But they're still called coterminal. So like those angles that I had drawn there, 0 degrees, 360 degrees, minus 360 degrees, those things are all coterminal. They all share the same terminal side. All right, well, so that would be 360 degrees. What if we didn't do a full rotation? What if we only say went halfway? All right, so here's our initial side. I'm gonna go ahead and rotate it. But we're going to do half a rotation. All right, well, so what would that angle be? Yeah, boom, getting a bunch of 180s. So that's your 180 degrees. You notice I also always write the little degree symbol. That's super important. Make sure anytime you're in degrees, you do that. All right, so that would be 180 degrees. That's not the only way to get our terminal side here. We could have gone clockwise. It looked like the exact same picture, except our arrow would be down here, right? That would be a negative 180 degrees. I could do an extra spin. That one's not 180 anymore. What would that one be? If I do full rotation plus a half? Beauty, there's 540. Yep, so that's 1.5 rotations. That would actually be a 540 degrees. Again, it's coterminal, but we're actually able to measure it because we're keeping track of rotations. All right, so this is what leads to the good old right angle being 90 degrees. So you remember your good old right angles from like squares and the like. Suppose that we start in our initial side in the standard position, but we just do a quarter of a rotation. All right, so we just go 1/4 way, or way around. There's your 90 degrees, also known as the right angle. So you guys are probably pretty comfortable with degrees, yeah? Thumbs up? We're used to that? All right, well, degrees are boring. I'm just gonna tell you, degrees are boring, and degrees are completely useless in calculus. In my calculus class, in fact, I outlaw degrees. Only time we can talk about degrees is when we're talking about temperature. All right, if we're talking angles, we're gonna do everything in radians. So let's talk a little bit about what radians mean and how those work. So first things first, let me just define it for you. Okay, so 1 radian, this is the angle necessary to create an arc length equal to the radius. Well, okay, so it's the angle necessary to create an arc length equal to the radius. Well, as soon as I put up the word radius, you probably started thinking about something that's not a triangle. Hopefully that kind of made you think circle, right? Well, arc length also has to deal with a circle. So think about this. Instead of a ray, let's just go with a line segment. Okay, so notice that I'm not putting an arrow on this. It's ending. And I'm going to go ahead and rotate it. And think about the circle that's being formed by that point. As that rotates, this dot moves, right? And if we kind of keep track of all the places where that dot had been, the next thing you know, we get a sector of a circle. All right, well, that's what this all means. All right, so we've got our radius. That's the size of the circle, right, from the center to the outside. And 1 radian is such that when we look at the arc length, which is that curved distance out here on the end, that length is equal to the radius. So, yay. That's how we define radians. So 1 radian, it's 50 something degrees. I don't remember exactly off the top of my head, but we can calculate that here in a minute. But it's going to be the angle such that that arc length that gets longer and longer and longer eventually becomes the same distance as the radius. So imagine you had like a measuring tape or a piece of string and you put it on that arc and you come down here and stretch it out, it's exactly the same length. So that's the definition of a radian. It's the angle needed to create your arc length equal to the radius. Okay, yay. But with that definition, we can figure out what one rotation is. So I want you to think about this. If you do one rotation, kind of like what we're doing here, but we go ahead and continue this so that we rotate all the way around. What is that arc going to look like? What is the outside going to look like if we do one complete rotation? Well, if we just kind of build it here, you know, so we got our circle, right? All right, thanks, Kai, for that. Yep, we got a circle. Now, what's the arc length of a circle? We have another name for that. Do you know what we call that, the arc length of a circle? Thanks, Adam. Yep, that's the circumference. And if you remember your formula for the circumference, we know that the circumference is equal to 2 pi r, right? So whatever the radius is, you multiply by 2 pi, and that gives you your total arc length. All right, well, remember what the radian is. It's basically the angle that we need to get an arc length equal to the radius. So the question is, how many radii lengths do we get if we go all the way around? Well, it's staring at you right in the face. It's right there. You look at that formula, circumference is equal to 2 pi r. It's 2 pi radii all the way around. So in radians, one rotation is equal to 2 pi. So if you've seen that before, and some of you may have seen the radian idea that there's 2 pi in a full rotation, now maybe you see why. Just by the definition, the way that we define it, it has to be. All right, so all those things that we did before when we had measurements of degrees, like with the 90-degree angle or the 360-degree angle, we can actually do that in radians now. So let me show you some examples. So I'm not going to bother with the full rotation because we already know that's 2 pi, but let's go back to this one where we're in standard position. We're going to go around counterclockwise so that we go halfway around. What's that going to be in radians? Yeah, thanks, Jessica. It's just pi. That's an angle of pi. You notice I didn't put a little degree symbol on there because it's not pi degrees. It's pi radians. It's just pi. All right, what about the good old quarter turn? The right angle. All right, well, now if we think about that one, oh yeah, there we go. So Benjamin just gave me pi over 2. This angle is going to be pi over 2 radians. All right, so Benjamin, do you mind telling me how you know that, pi over 2? If you don't want to type, you can unmute yourself. Oh, you remember the unit circle. So we got a cheater. We got someone who already knows a little bit more than he should. All right, I'm just, that was a joke. I joke all the time, man. So, all right, Mariola, so you just said 2 pi divided by 4. Yeah, think about it. We just did a quarter circle, right? This is 1/4 of a rotation. So 1/4 of a rotation is going to be 1/4 of 2 pi, which then becomes pi over 2. And you can think of it, we did the same thing over here when we did half a rotation. We did 1/2 of 2 pi, and that equals pi. So if you know what the amount of the rotation, you can always multiply 2 pi by that amount. So if you do 1/6 of a rotation, 1/6 times 2 pi, 1/10 of a rotation, 1/10 times 2 pi, and so on. Anyway, so that's how radians work. I know that at the start, you're not going to be super big into radians. So we will use degrees, but I'm going to kind of wean you off of them kind of quickly. I'm going to try getting you into radian mindset because it's going to serve you better in future classes. All right, well, if you want to bounce back and forth, we actually already have the conversion right here. The 360 degrees compared to 2 pi. You can actually use that conversion factor to change any angle from either degrees to radians or vice versa. So for example, what if I told you, I'm going to give you an angle, and I want to introduce something else to you really quick. When we represent angles, we usually use Greek letters. This is kind of an homage to the Greeks because they were the kind of the creators of geometry. And so it's not uncommon for us to use Greek letters. So I want to show you some of the more common ones that we're going to use. First one is this guy. So it looks like a 0, circle with a line through it. This is the Greek letter theta. It's going to be primarily what I use for a generic angle. It's kind of like x in algebra. You know, when you have a variable and you're like, well, I'll put anything in, I'm going to put in an x. That's what the theta is going to represent usually. Okay, so we're going to use theta a lot. Another one we're going to use, it's like theta, except instead of a horizontal line, it's got a vertical line. And that line usually goes through the circle. This is the Greek letter phi. P-H-I, phi. Some people do call it phi. Depends on who you are. But I go ahead and I'll say phi. So you want to say phi, that's cool. Phi is fine, but never pho or phum. No, nothing. Jack and the Beanstalk, phi, phi, pho, phum. Yeah, all right, never mind. Anyway, so there's phi. I just got to tell you real quick, hold on a second here.
Okay, so hopefully you can see me now. I just got to talk to you for a second. This is the weirdest thing for me in the world because I'm talking to myself and yet I'm pretending like I'm not, but I really am. And I keep trying to watch you guys and see your faces and what's going on. And for some of you, I can read, other ones I can't. Some of you are stepping away. It's just crazy weird. So for those of you who don't know me, I am like the king of dad jokes. Constant stream of them in class all the time. The fee, fi, fo, fum thing was another one of those. So you're going to get them. It's going to be super awkward, like worse than normal, but I don't know that I can stop myself. So anyway. All right, well, I digress. Let's get back to class here.
All right, so hopefully you can see the whiteboard again. Anyway, so we've got theta, we got phi. These are the two big ones that are generic. Yes, dad joke, man on his home turf. That's very true. This is kind of like X and Y. You'll see these a lot. The first angle will usually be theta. If you need a second one, you'll throw in a phi. But those are not the only ones you'll see. You'll also see this guy that looks like a little fish. All right. This one is alpha, which is the first letter in the Greek alphabet. So just remember the one that looks like a little fish, that's alpha. All right. You'll also see what looks like a kind of a curvy B. And this is beta, which is the second letter in the Greek alphabet. And then another one, the third letter in the Greek alphabet, the way I draw it looks like a little fish that's swimming downward. Doesn't always look like that in text, but this is gamma. So you'll see these a lot as well, just like we often see ABC when we're listing things out. We'll use alpha, beta, gamma, just in order. The next one is delta, then epsilon, and the like. But usually we don't go beyond 3. You can probably guess why we don't go beyond 3, because if all we're doing is measuring triangles, well, there's only 3 angles in a triangle, so we're not going to have to get past the third one, alpha, beta, gamma. All right, so these are the main ones you're going to see. We'll run into other ones from time to time, like omega, which is the last one that's used in certain things. Depending upon how far you go in math and science, you'll see all kinds of stuff like radioactive decay, for example. I teach modern physics a lot. There's alpha decay, beta decay, and gamma decay. Alpha, beta, gamma. Anyway, so, real kind of interesting thing. You may not have ever thought about this. This has nothing to do with math, but has everything to do with the Greek letters. So you know when we talk about learning the alphabet, we talk about learning our ABCs, right? Well, in Greek, you'd learn your alpha betas. I don't know if anybody just caught that, but check out the word alphabet. That's where the word alphabet came from. Just, you know, fun fact. So look at that. You're taking trig and you learn a little bit of other stuff while we go. So alpha beta, yeah, you learned your alpha betas. You learned your alphabet. Fun fact. All right, well, anyway, so here's how we're going to do this. Let's say I give you an angle. Let's see if we can convert it. All right, so I'm going to keep our conversion factor. I'll try to make a little space. I'm going to leave this up for just a second to make sure everybody's got it. But like, let's say I've got an angle of 2 pi over 3. So that's an angle. Is it radians or degrees? What do you guys think? Okay, so most of you guys are guessing radians. And I'm guessing it's a guess, right? What made you think that it was radians? All right, so a bunch of people chiming in with pi. Good, I figured that's what would make you think that. Turns out that's not how I know that this is radians. The way that you know that this is radians and not degrees is there's no little symbol. If there's no symbol here, radians. If there's a symbol, it's degrees. So I could have, we're not going to do this one, but we could have had 2 pi over 3 degrees. It's a very different angle. It's actually much smaller, okay? But that's how you can tell the difference. So you got to be really, really careful. If you have degrees, draw the little circle. If you don't draw the circle, it's radians. I think this is probably one of the reasons why I like radians better as well, is I have to write less and I am terribly lazy. All right, well, let me just show you how we can convert this from radians to, to degrees. All right, so we've got our conversion, but we want to take this from radians to degrees. I don't know if you've run into this in like a science class or anywhere else where you've done conversions, but all you have to do is multiply by a fraction that holds your conversion factors. Our conversion factors here, 360 degrees equals 2 pi. We can create the ratio 360 degrees over 2 pi, right? That's the conversion ratio. Notice that it can be reduced. It's actually same as 180 over pi. But this is our conversion ratio, and we're either going to multiply by that or multiply by its reciprocal. So if we want to go from radians to degrees, we're going to multiply by 180 over pi. whatever you're going to, make sure that's on top. So we're going to take our 2 pi over 3, multiply it by 180 over pi. So notice some things, the pi's cancel, the 3 goes into 180, right? You do your computation here, and we end up with 120 degrees. So the radian measurement, 2 pi over 3, is the same as the angle measurement, 120 degrees. Oh yeah, Amber, you did a ton of this in chemistry, right? Bouncing back and forth between everything with moles and grams and all that good stuff. All right, so if you want to go the other direction, like I said, it's just the same ratio, we just flip it over. So let's do this. Let's take one, I'll do it over here. Let's say we've got a theta of minus 40 degrees. All right, so negative just told us that we're actually going clockwise, but all right, so we got negative 40 degrees. So let's convert it. We're going to take that negative 40 degrees and we're going to multiply it by now pi over 180. Again, we're going to radians, so we want the radians on top. All right, so we can go ahead and do this computation and get it. I just want to let you know that if we can, we like to leave our radians in multiples of pi. Okay, so if you're going to use your calculator on this, don't put in a pi, just take the 40 and divide it by 180. We tend to like just simplified fractions. So if I were to divide both of those by 20, for example, I'm going to get minus 2/9 pi. So negative 40 degrees is the same as minus 2/9 pi. All right, so converting, pretty simple. We just bounce back and forth by multiplying by 180 over pi or pi over 180. This is going to be especially helpful for you early on when you have a radian angle, because like when I put 2 pi over 3, most of you probably had no idea what that was. No clue how much of a rotation or anything. But I put 120 degrees and you probably are pretty comfortable with it. So just realize that sometimes that will help. You can convert it to degrees. The more you use radians though, the more you're going to see that and go, oh, I see what I've got. Plus, remember this, if there's 2 pi on top, it's really easy to figure out. Because since 2 pi is a full rotation, this is 1/3 of a rotation. This one that was 2 pi over 9, that's 1/9 of a rotation going in the clockwise direction. So you're going to like these fractions of pi that have 2 pi on top, because it's going to be pretty easy to figure out what portion of a rotation that gave you. All right, so feeling okay with the conversions? I know radians might feel a little bit weird, but we're all right. Thumbs up. Questions? Will you need to memorize these conversions? So need to, I'm going to say no. Should, yes. Will it make your life easier if you have them memorized? Absolutely. Obviously, like if this was a face-to-face class, when you came in and you took your exams, I don't let you guys have note cards or anything, and so I would expect that you would have this memorized. Obviously, on any kind of an exam or quiz I give you guys, you're going to be able to use a sheet or anything. So you don't have to have it memorized, but it's going to become second nature. I promise, Amber. You'll get to the point where you don't even think about it. The 180 to pi ratio is just going to be a thing that you've got. Okay. All right. That actually just reminded me, because I mentioned quizzes. Something that I am probably going to put on quizzes or exams is a secret word of the day. So every one of these lectures is going to have a secret word of the day peppered in it somewhere. Obviously, if you don't watch this real time, you can still watch it at another time and get the secret word. It's basically my way of trying to get you guys to go in and, you know, actually watch this stuff. So let's see. I think the secret word of the day today is going to be calculator, just because my calculator is right here. All right, so the secret word of the today is calculator. So make a note of that. I'm going to write it down on my little list of secret words as well. So get ready for bonus points on quiz or exam or something asking you for words of the day. All right, so word of the day, calculator. Let's see, so Bella, so we multiply the reciprocal of 180 degrees over pi for converting to degree. Okay, yeah, so if you're going 2 degrees, right, when you go 2 degrees, you want the degrees on top. All right, so radians 2 degrees. If you go degrees to radians, you want the radians on top. So we're going to have pi over 180. Okay, so it's all about where you're going. If you remember where you're going, you put that on top and you're good. All right, any other questions before we step off onto another topic here real quick? All right, so again, I'm going to go with silence is golden. All right, so now we've got an idea of rotations. I'm going to show you some other things we can use angles for that are not triangles, some more geometry, and a little bit of physics even. That's the other thing you should know. I mentioned I teach physics as well. I'll bring in a lot of physics examples. My specific stuff was oceanography. I did physical oceanography. I looked at how tides move sediment, and there's a lot of trig in that. So be prepared to see some real examples of trig in use. So if you're not really a sciencey person, I apologize in advance, but well, them's the breaks. All right, so first some geometry stuff. You remember when I mentioned that radians were defined by arc length? It turns out that there's a formula that relates arc length to the radius and stuff like that. So I'm going to first give you here the arc length formula. So suppose that we have a sector of a circle. Now, if you're not familiar with what that is by those names, I know you're familiar with it. A sector of a circle is a piece of pizza. Okay, that's a sector of a circle. It's a wedge from Trivial Pursuit. It's a slice of pie, whatever. Okay, this is a sector of a circle. So the arc length, as I mentioned before, is actually the length of the curve out here. We use the letter S to represent arc length. Don't ask, I don't know why, right? I don't know the rationale behind that, but we've got that guy S. Now, I want you to think about this just for a second. What might make S bigger? What can we change about this sector to make the arc length larger? All right, let's see. Adam just threw out the radius. What do you guys think? If the radius of this circle was bigger, would the arc length be larger if I rotate the same? Yeah, so like I said, yeah, go farther away from the vertex. That's basically the idea of like pizza. Think about pizza. And let's say they slice it perfectly. I know they never do, but suppose that they sliced it perfectly into 8 equal slices. If you get a small pizza versus a large pizza, those larger pizzas are going to have bigger pieces, right? The bit of crust on the outside. Sorry about that, Quinn. I probably shouldn't talk about pizza at 12:30, right? But the larger the R, the bigger that S is going to be. Okay, so when we create this formula, we should expect that it has something to do with R. All right, now, can you think of something else we could change that would make this arc length bigger? something other than the radius. I'll even go ahead and mark an R here because we know that's going to matter. All right, so Bella just threw out angle. What do you guys think? If I make that angle bigger, is it a bigger arc length? Yeah, it seems kind of natural, right? If I think about if this angle was smaller, if I came down here to a smaller angle, that arc length is much shorter. So it's going to depend on the angle as well. So let me go ahead and put an angle here, theta. So the question is, what is that relationship? We need it so that as theta gets bigger, S gets bigger. We also need it as R gets bigger, S gets bigger. And I don't know if you remember from algebra ever learning about variation or anything like that. We would say that S and R have to be directly proportional or in direct variation. Same thing with S and theta. But let me show you how we're going to build this. We're going to set up a ratio. And what this ratio is going to be, it's going to be arc length to angle. Okay. So let's think about it for this circle. I know its arc length is S. I know that its angle is theta, because that's how I've got this drawn, right? So that's S and theta. Now, what I want you to think about is, what if we did this for a full circle? Okay, so now, here's our S. It goes all the way around. What's the angle for a full circle? Well, let's do this in radians. Let's go radians. So for a full circle in radians, it's going to be 2 pi, and the arc length was the circumference. So just notice what I built here in this little proportion is that the second one is for the circle itself. The second one was for the first one was for the sector. All right, so we just said arc length versus angle for the sector and for the circle. Well, let's solve this for S. So a little bit of quick algebra. 2's are gone, the pi's are gone. I just have to multiply my theta onto the other side. And check out this beautiful, and I know I say a lot of things in math are beautiful, but this is beautiful. This beautiful equation relating arc length to radius and angle. All it is you multiply the angle times the radius, times the radius. Cool, huh? S equals R theta. One big caveat though, make sure you remember that this is in radians. Okay, actually, that's so important. Radians. I'm even going to yell it. Radians. Make sure you're in radians. If you try to do this in degrees, if you take your degree amount and multiply by your radius, you are going to be very wrong. Right? In fact, you're going to be off by pi over 180. So make sure you convert it to radians first. But if you've got that, it's actually this easy. All right. So S equals R theta. And I'm going to anticipate Amber's question, although she may not ask it this time. Do you need to memorize this formula? Again, no, don't need to. Should you? It's going to be really useful in lots of places. So if you've got it down, you're a little bit better off. But it's easy to rebuild it if you have to. Just build this ratio. So let me show you how easy it is to calculate the arc length. So as an example, let's say that we've got a sector of a circle that's got a radius of 10 meters. So maybe we've got like a circular field. You know, like when you're driving over the hill coming down to Carson Valley, you can look down, sometimes you see those big circular fields from the way that they irrigate it. Well, let's say we've got one that's not a full one, but it's just going to be a portion. But we've got a 10-meter radius, and we've got an angle of 135 degrees. So I want to know how long is the arc length of that sector. And from an applied perspective, if we're talking about like a field, this would be, we're trying to put a fence out on the edge of that field. So basically, here's our picture. Let's put our initial side at 0. So 0 degrees, we get a 135. That's going to be over here, right? Somewhere in that general area. Think about what happens as we rotate. A quarter turn is 90 degrees. Another quarter turn is 180 degrees. This is between 90 and 180, so we're somewhere in there. All right, so we've got this, but it is a sector of a circle. So we've got this guy, right? All right, so let's see if we can figure out what that arc length is. So all we need is S is equal to R times theta. But like I just warned you, I can't multiply by 135, because it's not in radians. So we're going to have to convert that first. Well, we've already seen how to do that. We'll take that 135 and multiply it by pi over 180. All right, so, oh, Tiva just already gave me that angle. Nice, that's 3 pi over 4. It does reduce. Turns out you can divide both of those things by 45 when you get 3 pi over 4. So we're going to put that over here for our angle. So we've got 10 times 3 pi over 4. So that arc length is going to equal 15 pi over 2. If you reduce that fraction down, right, the 10 and the 4 reduce. But since this is actually an arc length, we probably want to get a decimal approximation for it instead of having the pi value. And my trusty calculator just spit out 23.56. And I'm going to go ahead and put a unit on there because as a science guy, it kills me not to. So we get around 23.56 meters. So that's how long that outside would be. If you were just to go start walking it, you would have to walk almost 24 meters to get from end to end. All right, so nice. Got a nice little formula here for arc length. Turns out we can actually also calculate the area. That'd be another thing we might care about. Like if we go back to the idea that this is some sort of a field, we might need to know the area to figure out how much seed we need to plant, how much fertilizer we need, that sort of thing. So we're also going to build an area formula. So we've got our arc length formula. I'm going to go ahead and put that up here at the top. I know you may not be able to see it right now because of maybe glare or angle, but this way it's out of the way. I can reference it here in a minute, but there's our arc length as S equals R theta. Let's see if we can build an area formula. So same idea, exact same idea. Let's see if we can figure out the area of this thing. And just like before, it shouldn't surprise you that the area is going to depend on R and theta. If R gets bigger, we have more area, right? A larger slice of pizza, if it's longer slice, it's got more actual pizza to it. Theta is also going to make it bigger. So we should expect whatever our formula is to be dependent upon those as well. So just like we did before, let's build a ratio here that's going to be area to angle. All right, so area to angle. For our sector, our area is unknown, but we know our angle is theta. So let's try and do the same thing as we did before, which is equate this to a full circle. So if I did a full circle, its angle again is 2 pi. What's its area going to be? What's the area of a full circle? You guys remember? Kiva just gave me pi r squared. Beautiful. Yeah, it's just good old pi r squared, right? You know that horrible joke. No, pi's aren't square, they're round. Okay, well, area here is pi r squared. So for the full circle, we've got this ratio. For the sector, we've got this one. And we're going to do exactly what we did before, which is solve that guy for A. So the pi's cancel. And then I want to multiply by theta. So I'm going to get A is equal to r squared over 2 times theta. And notice that it does depend on r, and it does depend on theta. But r is more important. Changing r is more important than changing theta when it comes to area because of that r squared. So I don't remember it this way. The way I remember it is the area is equal to 1/2 r squared theta. And that's what I recommend that you remember. This one, you're not as likely to remember or memorize as like the S equals R theta, but it's pretty handy. Again, theta must be in radians. Exclamation marks, right? In radians. But if you're in radians, this is how you can find that area. So let's go back to that same circle sector that we were looking at, the big field that was 10 meters in radius with an angle of, well, we have 3 pi over 4. Let me show you how we calculate its area. So the area of that thing, if we go back to that example, it's going to be 1/2 times 10 squared times 3 pi over 4. Okay, so that's our 1/2 r squared theta. It's that same sector circle, circle sector that we were looking at before. So again, put this into your calculator. And my magical black box, at least I hope this is right, I got approximately 117.8, and this one would be square meters. So just as easy to use, we just have to make sure that we're in radians. All right, so another thing that we can do that involves angles, but sector is a circle. So I'm going to go ahead and put this up on top here too. So the sector. All right, so now the next time that you get a piece of pizza or something like that, oh, you're going to look at it differently, I promise. And just remember, bigger R, way more effective in terms of your A. Like, I don't know if you've noticed that. Like when you go to get pizzas and they got the sizes of them, the radii don't increase that much. Like go to any website, you know, Blue Dog, Round Table, whatever, and you look at their sizes, and it'll be something like small, medium, large is like 12-inch, 14-inch, 16-inch. You'll notice that there's not a huge change in your R, but it does increase the size immensely. So just something to think about next time you're eating pizza. All right, I want to share one more thing with you, application-wise, and then we're going to call it. And this is related to the arc length. And this is a good physics example. This is what we call angular velocity. And I'm going to put here angular velocity versus linear velocity. All right, so velocity, you probably know about that, maybe not by that name. most people think of this as speed, right? Velocity, speed, that they're equivalent. They're not quite equivalent. We'll talk about that when we get to chapter 10, the difference between like velocity and speed. But for right now, we can go ahead and call it the same. So linear velocity, that's speed like, whoa. Sorry about that. All right, sorry about that, guys. My phone dropped, I caught it, and in the process, I opened up another window. All right, can you guys see the board again? We good? Thumbs up? All right. Okay, so linear velocity, it's like what you think of, miles per hour, feet per second, meters per second, anything like that, okay? So linear velocity just means it's your speed when you're traveling in a line. Duh, all right? So that's linear velocity. So linear velocity, we're gonna call that V for velocity. Now, angular velocity, what this is, we define it as the change in angle divided by the change in time. Linear velocity is a distance per time. That's why we write miles per hour. It's a certain distance that we've gone over a certain amount of time. Angular velocity is angle with time. All right, so the letter we use for angular velocity is this. It is not a W. I know you think it is. It's not a W. This is an omega. It's a lowercase omega. Greek letters have capitals and lowercase, just like the English language. This is the lowercase omega. Some of you may know omega better as this one, the horseshoe looking thing. That's the capital omega. Okay, so this is capital omega, this is lowercase, but we use lowercase for angular velocity. So angular velocity, it's defined as an angle over time, whereas linear velocity is a distance over time. So that's why we actually call these things velocities, or angular velocity, because it's the same kind of form, it's just it's a change in angle compared to a change in position. All right, angular velocity really only matters when we have something rotating. So applications of this would be things like the Earth going around the sun. We have an orbital angular velocity. There's also a rotational angular velocity of the Earth as we spin around in a day and things like that. So anything that's rotating, you have angular velocities. All right, so what does this have to do with anything? Obviously, notice it does depend on angles, and since we're talking about angles, it kind of makes sense. But I want to show you how these things are related, how linear velocity and angular velocity are related to each other, because they are, and it's actually a pretty simple relationship. So I'm going to come back up here to the arc length formula. So we'll leave our omega and our V down here for a second. So come back to this. We're going around in a circle. Okay, so maybe this is like a satellite that's going around the Earth, something like that, that's moving in a circle. Now, in terms of how fast it's moving, the way you think velocity, it's the distance that it's traveling over time. Well, since we're moving on a curve, this velocity, it's your arc length over time. All right, so that's your linear velocity. So basically, when we're talking about like the ISS, International Space Station, how fast it's going, we basically look at what portion of its orbit does it do in an hour, and that would be its speed, which is incredibly high, by the way. I don't know the number off the top of my head, but you would just take that arc length and you would divide it by the amount of time. Okay, so let me go ahead and draw in an angle here. So the omega, again, is going to be theta over time, because it's just that angle over that time. But you may remember that we have a relationship between arc length and angle. If you don't, it was that one up above. Oh, hey, thanks, Trayton. I just put up that the ISS is moving at 4.6 miles per second. Just think about that. That's going from the Y to state line and a little bit more in a second. That's crazy fast. All right, well, check this out. S is equal to R theta. Let me replace that in here. So we're going to get V is equal to R theta over T. I'm just going to rewrite that. Write this as V equals R times theta over T. And theta over T was equal to omega. So it turns out that we get V is equal to R times omega. So basically, if you want to figure out how fast something's traveling on a circle using, linear speed, if you know how quickly the angle is changing, square omega, you can multiply it by R and figure out its speed. So I've got some numbers that I worked out. I just want to go ahead and show these to you. And let's talk about points on Earth that are rotating, right? So first things first, just so you know, the Earth isn't actually a sphere. I'm not saying it's flat. I'm not saying it's flat. It's not a sphere. It's what we call an oblate spheroid, meaning it's been squished, right? Because of the fact that it's rotating, it's kind of squished down. It's more like an egg shape. We don't really notice it that much because it's pretty circular, it's pretty spherical, but it does bulge at the equator. It's kind of a weird thing. So equatorial radius is not the same as polar radius, but we're going to go with that it's a circle for this. All right, now imagine, we'll look at the Earth from the side. So up here is the North Pole. There's the South Pole. We got the equator running around the center, right? So think about being on the equator. As the Earth spins, that's what gives us night and day, right? As the Earth spins, you're moving in a big circle. Well, the same thing is true for us up here at Tahoe. So Tahoe, we're up at 37 degrees, 39 degrees north. So we're up a bit, but we also do a circle. It's just going to be a smaller one, right? And as we move closer to the pole, that circle gets smaller and smaller, but we're traveling circles. So what I'm going to do is actually calculate how fast someone on the equator is moving in terms of their speed compared to someone at Tahoe. Now, in order to do this, we need to know two things. We need to know the angular velocity, omega. And we also need to know the radius, the size of these circles. So I went ahead and got these numbers earlier. For the equator, and I'm doing this in miles because I think if I give you a number that's in miles per hour, it'll make more sense to more of you. This also goes against my better judgment and my instinct because as a science guy, we do everything in metric, but we're going to go miles. So on the equator, that radius down here, it's about 4,000 miles from the center of the Earth to the surface. When we're up at Tahoe, the radius to the center of the circle that we're traveling, this guy, it's a little bit smaller, and it's around 3,108.6. Oh, too low? Okay, thank you. And run it back up here. So we're definitely traveling a smaller circle than those on the equator. All right, so where I got those numbers You can just try, well, okay, the 4,000, do a Google search for radius of the Earth. The other one, I'll show you later because it requires some trig that we're not ready for. All right, but now we need to figure out what omega is. So remember what omega is. It's a change in our angle over a change in time. So just think about this. Over the course of a day, that's how long it takes us to do one complete cycle here. That's how a day is defined. So for us up here at Tahoe, our omega is going to be, we do 2 pi radians over 1 day. And so since I want this in miles per hour, I'm going to go 2 pi over 24 hours. So that's the same as pi over 12. All right, so that's our angular velocity. What about somebody standing down on the equator? What if we're down in Africa or South America standing on the equator? What's our omega there? Any idea how you could even get that? Because I don't know if any of you have ever been to the equator. I haven't. All right, well, here's the trick to it. How long does it take somebody on the equator to do a full circle? The same amount of time. A day is a day. Yeah, so Kai just put 24 hours. 24 hours, it doesn't matter who we are, right? Where we are on Earth, it takes 24 hours to go around. A day is still 24 hours. So it turns out that on the equator, their omega is the same, pi over 12. We're up here, omega is pi over 12, pi over 12, pi over 12. Doesn't matter where we are on Earth. The entire body is rotating the same way. So we actually get to use the same omega. All right, so if we go and we calculate that, so we're going to do V equals R times omega. That omega is going to be pi over 12, right? So same thing here, times pi over 12. But you put in the respective R's, you get considerably different velocities. So here at Tahoe, I know you're sitting in your chair, you're not actually moving, you're like, I'm not moving at all. Not true. You're actually moving at 814 miles per hour as you're going around, as the Earth is rotating. 814 miles per hour. You don't even feel it. You don't even notice it. It's just part of our everyday life. Turns out you're actually even moving faster than that if you want to compare like how fast you're going around the sun, how fast we're going around the galactic central point of the Milky Way, whatever. But in terms of the rotation on the surface of the Earth, we're moving 814 miles per hour at Tahoe. Now, you do the same calculation at the equator, and it ends up being 1,074. So a lot more, like 260 more miles per hour. Well, we were able to calculate that just by using a little bit what we've already figured out about angles. Remember how I told you that the Earth bulges fatter here than on the top? This is exactly why. I don't know if you ever played on a merry-go-round as a kid. Remember when you were out at the edge? Actually, hold on a second here.
I'm tired of not looking at you. All right, so remember when you were a kid and you're on a merry-go-round, when you're out at the edge, it's like way harder to hold on, right? When you're in the middle, no big deal. You can stand there all day, not a problem. But you're out on the edge and you're like hanging on for dear life. Is there a spin in it? That's because you're traveling so much faster. You've increased your radius. So you're going around a much larger circle in the same amount of time. You're traveling much faster. Well, you felt like you're getting thrown out, right? Like you're going out towards the side. Same thing happens on the Earth. On the equator, at the equator, we're getting thrown out. And that causes a little bit of a bulge. So interesting, yeah, hopefully. But it turns out that we're actually not spherical. It's actually, we're what we call an ellipsoid or an oblate spheroid. Anyway, whew. So I feel like I've been talking forever. I appreciate the fact that you guys hung on so well. Sorry about the couple times my camera fell. I'll see if I can do something about that next time. But just a couple of things as I wrap up. First of all, remember what trig is? Trigonometry. It's the study of triangles. We didn't do anything with triangles today. I just want you to notice that. We're not going to do anything with triangles for, well, I'm going to cheat a little bit and show you some triangle, but you're going to probably be surprised how little triangle stuff we do in this class. It's all about rotation. In fact, I think we should rename trig. It should be rotation-metry or whatever. So anyway, but hopefully you found this a little bit interesting. If you have any suggestions for what I can do differently, please let me know. And this is not just about today. This is like for the rest of the quarter as stuff goes on. I am totally open for ideas because I am, as they say, flying by the seat of my pants. I'm making this shit up as I go. And I want it to be a good experience for you. So please let me know. Also, if you are in a situation where you're concerned about your connectivity, you've got technology issues, please feel free to send me an email letting me know about any of that so that we can chat. I understand that these are weird times and a lot of weird stuff's going on. So I will definitely help you out as much as I possibly can. All right. So other than that, it was nice meeting you guys. For those of you that I've never met before, which is most of you. And I know it's weird that this isn't really a meeting, but it kind of is. So hopefully I'll get to know you over the quarter. But other than that, I will see you guys on Wednesday, same time, right? Same exact time. And look for this video up for you to be able to review and stuff. Hopefully, I'm not going to lie, it'll be up tomorrow. It won't be up today. I actually have class starting in 5 minutes with Diffie Qs and then physics class at 3. So I'm kind of busy today. But anyway, so with that, I'm going to have to run and sign off. But have a great day. And I'll hopefully see y'all on Wednesday. All right, so bye.